All right, so welcome to Department of Applied Math and Statistics Weekly Colloquium. So today we have Zhou, Professor Zhou from Colorado State University. He's currently an assistant professor in the Department of Statistics. His research interest is quite varied. He works on graphical modeling, game theory, optimization, and statistical machine learning. And also his work has been supported by NSF and DOE in recent years. But what I think is the biggest achievement of him is that he has two PhDs. One is mathematics and one is statistics. So we are done after getting one PhD, but he has done it twice. So he has gone over the whole process 2 times. So I think it's your biggest achievement. So anyway, so let's see what Rick has to talk about today. So today he's going to talk about estimation and inference of heteroscedasticity models with latent semiparametric factors for multivariate time series. Thank you.
Thanks, Social Theory's kind invitation. I want to thank you for the kind introduction. It's very nice to be in Golden. I have been in Colorado for 5 years. It's the first time. So it's a great opportunity. So today I'm going to talk about the estimation and inference of heteroscedasticity model with latent semiparametric factor for multivariate time series. So we're going to work with multivariate time series, and we're going to propose a new model for multivariate time series, and then we're going to propose estimation and inference, or statistical inference on the model. Then we're going to show the some theoretical result for the estimation procedure. And finally, we're going to wrap up the talk with some simulation and real data. Hopefully can convince you. The work is joined with, I didn't put here, it was joined with a student back to Colorado State. And he has done most of the proof. So first, let's have some motivation. What data we motivate the talk for? This is data collected from United States Air Quality Index website. This is the long-run variance we computed for the mean PM 2.5 concentration in 2015, collected at 129 monitoring sites across the whole states. And this is California, and this is nothing here actually, I don't know why. Nothing around, well, there may be one, but not too much around Colorado. Texas, a few, northeast. And this is Oregon, and this is Washington. So this is the US. So from this simple graph, this data, so what we have is people collect time series data from, actually this is weekly, or for each week it has 2 time points. So sometimes that's 3 time points. And for each of the monitoring sites, they collect a time series, and then we just compute what is the variance or long run variance for that time series, and we plot it, it's a single number. And then we plot all of them as 129 single number on this map. So this is time series, and it was somehow compressed in a single number. Let's look at how different those locations look like. And from this map, what you can realize that is the variability to the northeast. This is the main. I guess it's a very, relatively speaking, is small. The number is hard to read, but the color is self-explanatory. It's kind of a spread. And the variability to a little bit north. I think this is Montana. Okay? It's part of California. This is also probably this is Arizona. So it's kind of large. So for this plot, a data scientist or statisticians, I will say, okay, seems that conditional on where you're going to collect the data, the variability or variation is different.
Can I ask you a question? Just to make sure I understand what you're measuring. So you're measuring PM 2.5 weekly at each site?
Yes.
Just at one time per week, or is it the mean for the week, or the max?
Tuesday and Thursday. So Tuesday data, Thursday data.
Okay, so you measured it just one time on Tuesday and Thursday, or is it the mean?
The data is average across the whole day.
So it's the mean on Tuesday and then the mean on Thursday, and then you average those two to get the mean for the week?
No, you got the mean for Tuesday of that week.
Oh, okay.
So Tuesday week 1, Tuesday week 2, Tuesday week 3.
Oh, okay, so it's the mean for Tuesday each week for 100.
For each Tuesday.
For each Tuesday for however many weeks, and you compute the variance of those means.
Yeah, not exactly variance, long run variance, but
Okay. Okay, now I understand.
And also, Rick, I have one question. So you just said that you were looking at 120 something different locations, right?
yeah, 109.
Yeah, 129. So you are just looking at the temporal part. You are not considering the spatial.
Yes, spatial is here.
But are you going to?
They are
consider
going
that?
to be modeled.
Oh, okay.
Yeah, but from here at least, yeah, just as the question, the spatial, this is spatial information, longitude, latitude. Okay. So from that point of view, yeah, monitoring set-wise, the conditional long-run variance are different, or spatially, different location give you different long-run covariance. Another example, not from this 129, but that's quite small, is this. This is a sequencing data, which we worked before. The paper itself is Nature, but the data is very interesting. This is RNA-seq, the next generation sequencing data, RNA-seq data, collected for maize. These are some prototypes. Okay? This is 30 different prototype from rice. So people study the genetic dynamic across time. This is a time curve of rice, and then they come up with certain prototype. They think, okay, this is a typical dynamical pattern for rice. So there are pattern 1, pattern 4, 3, 4, 5, 6, up to 30. Okay. There are some others which is noise patterns, so people even want. So this research this is a huge project. Part of it is try to study how C4 maize, C4 is a prototype, how C4 maize align to those from rice, and try to do some genetic modification or some genetic study. But out of 14K genes, 14,000 genes, their dynamic was aligned, and you can see that. This is a time measurement, okay, this is time point. There are about 13 time points. So you have, how many curves do you have? Well, if I do not consider replicas, I have 14,000 curves. Each of the curve has 13 time points. And for some of the prototype, conditional on the prototype, for some of the prototype, the variability is huge. For some of them, the variability is small. For some of the variability is quite small. So, in other words, the variance structure or the variability of the temporal dynamic for these genes change according to which prototype they belong to. So conditional the prototype assignment or conditional to the prototype alignment, the variance change. So those two type of data, or those two data sets, among all the others, raise this question. If I have a huge number of time series, for example, I have 129 time series here, I have 14,000 time series here. Some of the time series is very long. In this case, 100 or even 200 time points. In this case, only certain time points. And all the time series has different variability, conditional on other information, which prototype, or maybe in stock, which sector come from, or which monitor site, how to model them, and how to understand the dynamic of the time series, and meanwhile how to model this heteroscedasticity, different conditional variance across certain covariate. How to model that? So that is our major motivation. Try to model those heteroscedastic time series. Try to model those high-dimensional heteroscedastic time series. So first challenge for modeling. We have two major challenges. The first one is heteroscedasticity. So by definition, that means the conditional variance of zero, also the cross correlation will change from subject-specific covariate. For example, if I look at the time series, it comes from prototype 1, or this stock comes from sector of energy, or this very particular time series of PM monitoring comes from location in somewhere in California. they are different from others. So condition on some subject-specific covariate, location, sectors, prototype class, the conditional variance of time dependency, or the distributional, the probabilistic structure, or the cross curve dependency change. How to model them? Can we not model them? It's your choice. You don't have to model them. If you don't model them, you have to pay a price, because we know there is something different there, and we don't consider that. Statistically, statistical inference without accounting this is inefficient. What does that mean? We're going to show that. We're going to rigorously show if you do not account them, that's not efficient. And we're going to use the concept of variance to specify what does efficiency mean. Another challenge is naturally come from high dimension data. Number of features is too large. I have 14,000 time series. Each of them only has 13 measurements. Even though they are not time series, that means I have 13,000 curve, and each of them only has 13 replicates. Small number of sample size compared to huge dimensionality. Model high dimension time series itself is very challenging, because you have to model the serial correlation. Not even mentioning there's also cross-curve correlation. How about the stock from IBM is correlated with stock with Google? And also the stock price within Google change. And the closer the two time points, the more correlated and the far away from each other or more apart from each other, the less correlated. How to model both cross and also within curve correlation. If you want to use a traditional parametric model, that is very hard. That means you have to introduce a huge number of parameters. At least to model the dependency across curve. 1,000 curve, the covariance matrix has 1,000 times 999 divided by 2. That's many parameters. That's a huge number. Well, unless you do regularization, using Lasso, using regularization, to introduce an actual sparsity, you can identify the parameter. Otherwise, not even mentioning inference. Estimation is hard. A few papers here, I think McVitie's and Shakti's recite some nice review paper on this topic. So to deal with these two topics, heteroscedasticity and also the dimensionality, the statistician mathematics statistician have been working on them for a long time. The effort on understanding of model heteroscedasticity can date back to the 1960s in econometrics. In the field of econometrics, people introducing so-called heteroscedasticity model to model those varying conditional covariance with respect to certain covariate. For example, I consider the simplest linear model cannot be simpler anymore. Y equals Z transpose beta plus a random term, and this random term has a variance, and they assume the variance is a function of some subject-specific covariate xi. This xi, for example, if only one component, that means each of the object or each of this observation I has its own variance determined by this xi. Okay, and this is the model proposed by Harvey in 1976 in Econometrica. It is a very pioneering work. Then, following by that, Box Hill and Professor Phil from Iowa State, Rin Carroll from Texas A&M, but at that moment it's not. They all propose different type of model. By relaxing this parametric form, expansion is too stringent. Who does not have to be that? So let's assume H is some known. This H has some known structure, but I have to estimate the structure. For example, come from smooth function class. Okay. Then I can estimate H using some non-parametric approach. Chungu from Purdue and Dina Wang from the University of Georgia, 2005 proposed non-parametric mixed effect model, trying to generalize their idea to include mixed effect. And Pan and Xue in 2012, they proposed random single index model, but generalize this eta x further to generalize this x to an affine function, a linear function. There are a lot of functions here, there are a lot of models here along this line. The whole purpose is introducing some function form to model the heteroscedasticity and allow that function change with respect to some subject-specific subject-specific covariate. So that's the idea. So that is all about heteroscedasticity model, and they are going to motivate our model. The next one is, even if you do that, how about correlation? All of this model does not deal with this correlation. They work with data which are independent. How about time series? How about temporal dependence? Where to put them? How about dependence across curve? How to put them? Those questions was answered by a factor model. Factor model in the language of linear algebra is just a low-dimensional approximation for a matrix. That is factor model. So it is modeling using factor is most frequently used method to do dimension reduction, to model dependency from different direction, especially for multivariate time series. This is the traditional factor model. YT is a multivariate time series. A is called the loading, and eta t is my factor. ET is some residual, some error, some noise, which cannot be modeled by A times eta t. So the covariance structure of YT is essentially A times covariance of eta t times A transpose. So by imposing some structure on A and also dependent structure on eta t, you can model the covariance of YT, where eta t and ET are independent. This model is called traditional factor model, proposed by Anderson from Stanford in 1963, then followed by others, for example, Chamberlain and Rosenshell in 1983. This is an econometrical paper. And also later studied by Zhou and Pan Yao and Lam from RSE. They all studied this model. Theoretical investigation of this model is well known, and also it was generalized to different kind of new model. For example, Ingo in 1981 proposed a distributed lag factor model to allow this eta t became a dynamic system to model that. And also others like Griffiths and Graham in 2006 and others like Gauche and Denson proposed Bayesian latent factor model. And simple dynamic factor model allow not only you consider YT, you consider another variable ZT together, they will evolve. So this is the factor model. A quick introduction, a quick review. What is the problem, or what is the application of factor model? They are widely used in statistics, or in data science, or in machine learning. First, they can do dimension reduction. Where is dimension reduction? It's A. A usually is a low rank matrix. So the number of parameters was greatly reduced by restrict the rank of this A. For example, if only rank one, then the number of parameters is hugely reduced. So it deals with dimension reduction. On the other hand, it can carry the serial correlation. How? Allow this eta t to be a time series. Then the dependency across time point was measured or was modeled by eta t. So factor model can do dimension reduction and also keep the serial correlation, and does not have to give any parametric assumption. But factor model has problem, of course. Some challenge on traditional factor model is this. First, if sample size or number of time point is very small, can you still do model? And if you can, how small is small? How many time point you have to collect? For 1,000 stock price, how many time point do I have to measure? 1,000, 100, 1 million? If I use that many time point, can I still estimate heteroscedasticity? Or can I still model that? Even if I can model that, can I efficiently estimate the systematic part? What do you mean by efficiency? You define efficiency, and you need to estimate that. And also, if you estimate the loading and the factor, that's A and eta t, when number of time point is small, you still have conversion rate. You need a non-asymptotic rate. And finally, how to model loading using other covariates. And meanwhile, can keep the satisfactory estimation accuracy. Those questions motivate our model. So that is our contribution. First, we propose a new heteroscedasticity model with a latent semi-parametric factor to model multivariate time series with growing dimension. By growing dimension, we mean the number of time series could be huge. We developed a computationally straightforward two-step estimation, which is called TOPE. Then this is a projection-based estimation to estimate the latent factor. You're going to see that. What does it mean? The latent factor or latent factor process and the loading. And then, the coolest part is we give a very careful concentration result. That is a non-asymptotic result. Now, to get that, you have to use some operator theory and also empirical process result. Then you can show that you can carefully give a concentration rate. Using that concentration rate, You can develop the further inference procedure and show that for the systematic part, I can get efficiency. Otherwise, that efficiency is very hard to develop. But finally, as a byproduct, we give a data-driven approach to estimate unknown number of latent factors. What is rank? Is rank 1, rank 2, or rank 3? Data say that. How to use data? We give a new method different from eigenvalue-based approach. So that is our outline. Now, our model. This is the simplest statistical model ever can be considered. This is a linear model. YIT equal to ZIT transpose beta plus epsilon IT. I is the number of curves, T is time point. Here, again, I say I is number of curves. You can consider I something else, for example, location. I is class. I is whatever you want. Okay? There are n of them, so there are n curves here, and each of them has T time points. And they are measured at the same time point. YIT is observation from I subject at time point T. ZIT is the p-dimensional covariate, which the p is fixed in this case. And beta is the regression coefficient. Our goal is want to estimate the beta and make this epsilon IT handle serial and also cross-curve dependency and also heteroscedasticity. How to do that? Epsilon IT is a stochastic process. It's going to be modeled in this way. We consider epsilon IT is a gxi times ft. So for each of the curve, there is a covariate xi, whatever it is, which sector you come from, or the volume of your company last minute, or location of this monitoring site, category of this, or prototype of this gene, or blood pressure of this patient. It's your choice. Now, gxi is a function which handles the heteroscedasticity. Different I have a different xi, so different curve have different xi, therefore gxi are different. Then, the serial correlation, just like the factor model, remember A eta t, that eta t was modeled by this ft. Ft is a process, it's a stochastic process. It's a latent factor process. So epsilon it is modeled by gxi ft. gxi handle the heteroscedasticity. Ft handle the serial correlation. And because gxi, because they have a product form, they actually mimic somehow the Coulomb expansion for functional data analysis. This is eigenvalue, this is eigenvector. Okay, I have this flavor. And finally, can this expression explain everything in epsilon IT? No, it can. So we'll assume there are some residuals which is independent from ft, UIT. In spatial model, this is white noise. Then the model will be written in this way: ZIT transpose beta. It's a p-dimensional vector times the p-dimensional vector, so this is a scalar. YIT equal to scalar plus gxi transpose ft plus UIT. Why have transpose? Well, I may have one function contribute to heteroscedasticity. I may have multiple of them. Well, I may have one, I may have two, I may have a lot. So here I have k. G1 is a function of xi. G2 is a function, gk is a function of xi. The only thing here is xi is a vector. For each of the variable, for each of the curve, I may have a lot of covariates. For this patient, I have blood pressure, I have height, I have demographic information, I have blood sugar, I have a lot of information. How to model them? The choice is quite a lot. For simplicity, we model them using an additive model. So gk is a function with d input. How to model that? There are a lot of different ways. One way we model them is summation L1 from d gkl xik. This is the generalized additive model by Peter Billman. If we look, actually originally by Hasty and Anti-Crown. If you look at this closely, this is just generalized additive model. Can I put this bivariate? Of course you can. Then the model is more complicated. You have to, yes.
Isn't this just like a GU and map, but the particular representation for the random effect?
There's no.
No, I mean it's similar to what GU and map
Oh, that's
propose, right?
Yeah, that's right.
for a particular representation.
Yeah, they have only one of them.
Yes.
Now I model gk in this way, so this is the k by 1 vector, and this is the 1 by k vector. So I have kft. I have k latent vector process. I have k latent vector process, and this is loading. Now a little bit of assumption: f and u are independent of z and x, and f is a k-dimension process of zero mean finite variance. UIT is error process of zero mean and independent from ft. Now there are two more questions to be answered before we proceed to estimation. The first question is, z and x arbitrary or different? Can they be same? Why we worry about this question? Because in linear model, y equal to x beta plus epsilon, we usually assume that error epsilon has nothing to do with this x. Otherwise, we introduce indigeneity. The estimation is always biased. That is a big problem in econometrics. Okay? So how, in this case, do you allow x to be same to z? I know u has nothing to do with z, and u has nothing to do with x to f. How about this part? You say nothing about x and z. Can they be dependent, or are they independent? Second question is identifiability. A times b. We taught our own students, you can a times b equal to 1. I have no idea what is a and b. A could be 3, b could be 1/3, a could be 2, a b could be 1/2. How can you identify G and F? That is a model question. Is this even a well-posed model? If it's not, we should stop here or put some condition there to make it well-posed. First question, can Z and X be dependent? The answer is yes, surprisingly, yes. Just because I have a function G here. Without the function G, the story is finished. X and Z cannot be dependent, otherwise they cannot be separated. Because it's G, so I actually artificially introducing some complexity to make a nonlinear to this function, to the function of X. So G, even though X and Z are very close, but after this function G, Gx is quite complex. It lost its original face, original image. So it can be separated from that Z. So this is our example. I consider ZIT with ZI0 plus ZIT1, and ZI0 and Xi may come from the same d-dimension distribution. ZIT is from other time series. So so ZIT and X is partially correlated. I only need one assumption to make this model still identifiable, which is this. I need G function living in a Holder space where there's no affine function like Z. We're going to specify the condition a little bit more. But the idea is G oscillated too much, or if G is very complicated, different from linear function. You have a straight line here, and you have some sine function here. Empirically, there's no dependency. There's a highly oscillated sine function, there's a straight line passing through. Empirically, there's no correlation between that sine function and also the straight line. Algebraic. So I need the algebra condition to make Z and X not overlap, even though Z and X come from same distribution. So that condition is a Holder space where there's no affine function like Z. And we're going to give this algebra representation later in condition part. And so with overlapping Z and X, actually we can test for indigeneity. So that's a byproduct. Second, identifiability, G and F. How to identify them? And we need to go one more step. We need to let the model stand in a matrix form. So this is the matrix form of my model. Y equal to Z beta plus GF plus U. There's only one observation. T equal to 1, there's only one observation. And this is actually the classical model. But this model, Z is known, beta is unknown, Y is known, G and F are both unknown. This is our model if there's only one observation. This is exactly the model considered by Chamberlain and Rosenthal in 1982 econometric paper. And they propose this condition. Under this condition, G and F can be identified. So ZF, U are uncorrelated, F is uncorrelated, F1 through Fk are uncorrelated with zero mean and unit variance. U1 through Un are independent from everybody else and also are uncorrelated with themselves. So
why do you need a Holder space?
I need to approximate the G because I don't know what the G is. G is arbitrary function, I don't know. So I need to do, Holder space guarantees C works. I need C approximation actually. That's why I need Holder space. So this condition can guarantee I can identify G and F. In practice, if I have data empirically, the model reads in this way. If I have T replicates, which are not necessarily independent, the model we propose is this way. Y equals Z times IT Kernel beta plus GF transpose plus U. Y is a matrix. Y is an N by T matrix, or S by T matrix, depending on how you look at it. There are N curves, each of them have T measurement. This is the linear component, GF transpose. G is an N by K matrix, F transpose is K by T matrix. And U is an N by T matrix. This is actually a realization of a two-dimensional stochastic process on N by T grids. You can look at it in this way. And if we ignore the linear part, this is actually nothing but just the factor model considered by Zhou and by Professor Bai and Professor Yu Ji in 2013. So to make G and F, this F is just has one vector. This is the matrix. To make the whole matrix identifiable, we need this. Almost surely for each n, 1 over TF transpose F is identity matrix. So F is uncorrelated. G transpose G is a diagonal matrix with distinct entries. With this condition, the Chamberlain and the Rosenchild condition, and also BMG condition, we can identify our model. Those are the conditions we need to impose. We don't need to prove them, the proof has already been done. So, identification condition about F is compatible with identifiability condition proposed here. We can identify G, H, and FH for some K by K orthogonal matrix H. This is rotation. Using bias condition, you can show this orthogonal matrix, which is in the middle of G and F. Look like this. This identity matrix plus small o of n and t. So if nt go to infinity, this H is almost an identity matrix. So asymptotically, G and F can be identified. So those are the identifiability condition. Now the model is done. I want to pause a little bit and talk about this is the model. Those are two conditions. So the roadmap is we have a model. The model has three components. First is the linear part, Z transpose beta. I don't care about that. I could care about it. It's about systematic, long-term behavior. Variability was handled by GF and U, but U is just residual. GF handle heteroscedasticity and also serial correlation. And also because I have K of them, so it handles cross-curve correlation. Within each of time, for each of the time point, all the curve cross are dependents, modeled by this G. But this model has a little bit complicated form, so we want to make sure Z and X can be overlapped. We impose a condition that holds space without affine function. We are going to more mathematically specify what does this condition look like. Also, we need G and F satisfy this condition and also Chamberlain condition. So I can identify G and F on the short. This is the model. Now, how to estimate it? First, two steps. We assume there is a beta. I don't like this beta, so I assume there's a beta. I have a beta, I can plug in beta, I can remove this systematic term from my data. So everything left look like this. Y tilde equal to GF transpose plus U tilde. G unknown, F unknown. But I know something about G. G is a smooth function. G can be approximated by basis function. Gx can be written as summation I from 1 to m, phi x times some coefficient. I can project it to in spline world, to basis function world. So I can consider a projection matrix to approximate the column space of G. That means I'm going to project it. There's P, the projection matrix in the paper. So the projection matrix basically comes from the basis function. So I'm going to project Y tilde using this projection matrix. And for the project data, I'm going to use the classical PCA. So I consider Y transpose PY tilde, Y tilde transpose PY tilde. And this is a T by T matrix. It's a T by T matrix. I'm going to do eigen decomposition of this one. If we are really careful about theory and also the details, this is not PCA actually. PCA is about N by N matrix, not T by T matrix. Or PCA is about a P by P matrix. We use the T by T matrix. because it will give us some advantage in theory, so we can show the consistency. N by N matrix is actually much harder. Using this T by T matrix, we can get eigen decomposition using the eigenvector to estimate this f hat. So f hat divided by root t is eigenvector, so I only get eigenvector and recurrent f hat. Once I have f hat, I plug in, I got a g hat. So this is the procedure. This is actually just a PCA, a principal component analysis. Once I got a g hat and f hat, what should I do? Well, fine. Plug them in and subtract them from y, or somehow using them to estimate the beta. How to do that? Compress all the time point. Now you have g, now you have f. Sum over all the time point, take average, and the model look like this. This model has nothing to do with t, because beta has nothing to do with t. The regression coefficient has nothing to do with t. So y bar equal to z0 transpose z0 is this, beta times g times that, times n plus this. Now g and f will be known because I already estimated them. Now, this
so
is
I missed your model for G here. You went through it pretty quickly.
G is
You have some basis functions.
yeah, G look like this. And then each GKL will be approximated by basis function. I didn't include that detail here, but yeah. So each GKL, for example, can be written as summation m from 1 to capital M.
So you had a P
Yeah.
and
P is a P. P is here. P has nothing to do with G. G is a K by T. Sorry, G is N by K. N by K matrix. I have a K function. I need to approximate the K function. Each of the function look like this.
oh, okay. So later on in your talk, when you were talking about taking P and the projection,
I'm not going to show what P look like, but it is in the backup slide.
you've already estimated G
Yeah.
using some
Basis
non-parametric.
non-parametrics.
Okay. All right. Okay. Thanks.
We can show the detail later. So once I have this model, then I can propose the two-stage projection-based estimator TOPE, which looks like this. This is just a generalized least square estimator. And we had all defined this way. So this is GRS. If I know what is the covariance structure of F, if I know what does the G look like, that's a linear mix model. If so, X beta Z U plus epsilon. But I don't know what is a U. Sorry, I don't know what is a U. I don't know what is a Z in the linear mix model. So I have to estimate them and using GRS to provide a further update of this beta. This is a two-step estimation of beta. Now, the coolest part, following is how well is this G hat, F hat, and beta bar? Do they perform well in theory? If well, how well? If well, does any requirement on T and N? How many time points can your model handle? 6 conditions. First condition to the theory, eigenvalue bound. Did you transpose? So eigenvalue is of order n. Okay, that is a typical eigenvalue assumption for PCA. Eigenvalue is diverging in the rate of n. Density of x, the covariate, is bounded away from 0 and infinity. You can always normalize them. I'll talk about this later. 4 and 5 are all about the sieve approximation. G function is live in Holder space, so I want to approximate it. Fine, and G is approximated by this. This is what Dodd asked. So G is actually approximated by this. BKJL times VG. VG is some basic function. Any basic function, spline, whatever basic function you want, as long as they satisfy this rate. And this rate can be easily satisfied by many approximation of non-parametric method. For example, 减轻的奥数乃馨 has a lot of this, very careful. And also UF time series. They are strictly stationary, strong mixing or alpha mixing, highly dependent. And the UF independent. And finally, I assume marginally UF are substantial. Okay? Gamma distribution, T distribution, chi-square distribution. So time series, we have heavy tail distribution. Not heavy tail, but slightly heavier than Gaussian. Now, back to this condition. What is number 3? This condition happened a lot in non-parametric work. This is high dimension, non-parametric high dimension. What is the number 3? This is new condition. This is what we mean by leaving a holder space without iFun function in there. 1 over nz0 transpose z0 has eigenvalue bounded away from 0 to infinity. Oh, sorry, there's a typo here. That is just eigenvalue condition for Gram matrix of linear model. This condition, PZGF is big O 1, is what we mean by holder space without iFi function. That means G function is quite different from Z. So this is the algebra representation. G function is quite different from a linear function, which is Z. Or G is different from the column space of Z. It has to be big O1, not small one. Otherwise, the previous model is not identifiable. Or you have to make Z and X completely have nothing to do with each other. So this condition will guarantee that you will have a consistent initial estimator, guarantee that your estimation procedure is consistent. Under this 6th condition, we provide the non-asymptotic result. First, concentration of F and G.
So is that Frobenius norm you have
Yeah,
there?
that.
Is that what the F is?
Yeah.
So it doesn't look like either.
P is the projection.
I'm trying to figure out if things are normalized or not. You have like a 1 over n G prime G there.
This is normalized already. G is a n by k matrix. The PZ is a projection matrix, but this projection matrix is already divided by T.
Yeah. So why is it bounded and not slowly growing? Because G is getting bigger.
It could grow, but at least it must be bigger one. It cannot be small one. So understand.
Okay. I guess I'd feel more
Using this
comfortable if there was a 1 over n in there, somehow pushing things down.
This one has this is a projection matrix.
Okay.
So it's already have a inverse over Z transpose Z inverse. It gives you a 1 over n over there.
Okay.
Hopefully, probably can go through the detail.
Yeah. All right. Okay, thanks.
So we can prove the concentration of F hat and G hat. So this is MSE mean square of F hat of F and the G hat and the G. And the theorem itself established consistent of F hat G hat. This is non-asymptotic. This is true for any n, any T, any P. And if we look at this one, we realize one thing, hey, P is fixed and G is small order of n. What is our conclusion? This one is always small one. Whatever T and whatever n. That means the model can handle any number of curve with any number of time point. You give me 2,000 stock, each of them has 3 time points, I can do it. You give me 3 stock, each of them has 1,000 time points, I can do it. The proof of this one is far away from trivial, but you can show it using that.
So are you assuming a specific number of derivatives for the holder condition?
I think the derivative is.
Oh, okay.
Yeah.
Okay, so
That is really not a big concern in this. Yeah. The hard part in theory is how to get this 1 over n and 1 over nt here. Because actually, I should back up. The projection matters. I need to use the projection to make sure this one, to make sure this one is not big or 1. If this is 1, it does not converge. So I need this kappa is larger than 4 as well. Actually, in this case, as long as larger than 4, it's okay.
Okay, I got you. Yeah. And that 20 is sort of mysterious.
It doesn't matter. It's just non-asymptotic rate, so it's anything.
Yeah.
It's
I
just,
mean,
I can put it equal 1.
if you put it in, you're going to get a question. so you're just saying it just comes out when you have that 4 on the holder.
Yeah, you can make this 20 has nothing to do with derivative. It's come from concentration.
Okay.
It could come from a few sets intersected to each other.
Okay.
You can make this 1. It's just a typical constant in a non-asymptotic.
All right. Okay.
And then, using this concentration of F and G, we can derive consistency and efficiency of top estimator. And that is quite new. Suppose J is this order with probability at least 1 minus delta. I have those two conditions. I have those two conclusions. First, beta bar minus beta tilde are to norm. It's non-asymptotic. Again, this result is true for any n, any t, any p. N could be 1, only one observation. I'm okay. This bound is on the same order, 1 over root nt. This is exactly parametric rate. That is the minimax optimal parametric rate. And this is small 1. Both of them should be concentrated around the 2 beta with a ball 1 over root nt. So they're both beta plus 1 over root nt. But they need to have a small 1 distance that come from here. The small 1 distance, first, this is estimation from F. This is long-run covariance estimation. And this estimation of G. So this is where this small 1 come from. All of these 3 terms are small 1. So they're small. Now beta bar is very close to beta tilde. Beta tilde, what is beta tilde? Oracle GRS with normal G and the variance structure of F. I know what does F look like. F come from normal distribution with 0 mean with that type of variance. G, I know it look like certain type of number. I even know what is the value of G. I have estimator know them. I don't, and my estimator is just as close as to you with a parametric optimal rate. This is the minimax optimal. Not only that, variance of beta bar minus the variance of beta bar tilde for this norm is bounded by 1 over nt. I know it's bounded by 1 over nt. This is 1 over nt. This is 1 over nt. But this f is small 1. So it's super small. That means asymptotically, this non-asymptotic show asymptotically beta bar is efficient, just as efficient as GRS. Therefore, optimal. Geometrically, it looks like this. We consider as a class of estimator look like this. Is all estimator. So remember previously there's a V here. Now I just replace the V by whatever V I want. I just give a V. Now the only thing I want is V alpha minus V L2 norm. The largest eigenvalue is bounded by alpha. Within this class, ORS is optimal in terms of efficiency. And top, our estimator is in this class with alpha replaced by F, ordinary square estimation. This square is always here, but with alpha is 1. So the B go 1. There are 2 distances. The first one is this. Beta alpha hat minus beta, this is 2 beta. It's always this is parametric distance. Everybody is within this distance, 1 over root nt. Everybody. You give me a matrix, whatever matrix you want. You give me a matrix as long as the distance, the largest eigenvalue between this matrix, the working matrix to the true one, is bounded by alpha. This is within this ball, root nt, 1 over root nt. But one of them is super close. That is our top. Beta hat alpha with small 1 is very close to GRS. This is basically what our theorem said. Everybody is within this ball. This is the true one. This is the parametric. This is the parametric ball. MRE. Everything is within here. But the distance to the beta GRS, some of them could be large. Our theorem shows that ours is super small. This is small 1. This small 1. So top is asymptotically theta f optimal. Now we've done one more theorem I want to show is this. We consider maximum norm. These are our maximum norm results, and the take-home message I want to give to quickly skip this page is, we show that if all the f, if there's no serial correlation, the way we estimate covariance matrix, we estimate the G and put G back, reach the optimal result, reach the optimal rate to estimate high dimension covariance matrix. So this is kind of like byproduct of our model and our procedure. I'll quickly go over inference, and we can easily show that top is asymptotic normal. This is kind of like standard Zhou theorem. And also conditional on ZTX, we can also show it is normal. That means we can draw confidence interval, and the confidence interval and the confidence set are given by this. Because I'm out of time, so I'm quickly jumping through this. I will demonstrate this model by some numerical study. We consider 50, n equal to 50 curve, 100 curve, 200 curve, 500,000, 2,000 curves. You can consider location, stocks, G, your choice, or patients. And T is 20, 50, 100 up to 1,000. So for example, 2,000 stock, only 20 times 1. Or 50 curve, each of them has 1,000 measurements. So that's all combination. Covariate Xij was sampled from uniform 0, 1, and G was considered by this. We consider the polynomial. This is exactly used by Wei Chen and Jian Qi in their 2017 paper. And ZIT, which is our covariate for beta, is sampled from normal distribution, like this, independently. And our innovation FA, F and U, we consider 3 types. First, F could be ID, or F could be AR1. In the paper, we also consider F is armor. And same thing for U, independent or AR1. Innovation could be normal 0, 1 or centered chi-square 5. And the same thing for UT, normal 0, 1, centered chi-square 5. And these are data. These are data generation. Sorry, chi-square 7. We compare our method with ordinary square estimation, GRS, which is used by John Story and Jeffrey, and also studied by Yao, and also the Oracle one with known G. So we consider the 3. And we consider the criterion, which is the MSE to estimate F and G, and also MSE to estimate the beta. And for inference purpose, we consider empirical coverage probability, maximum marginal length. This one guarantees that your confidence interval is right, it's valid. This one, the smaller, the better. That means you are more efficient. And we have some numerical study about selection of K, but not included this talk. So this is recovery of F and G. For F, you can see we almost form the red one is taupe, is our method. The black one is the true one. Know what is G to get F. Know what is G to get F. They're almost same. Okay? As n getting larger, they're almost identical. And to get G, you see that as n getting larger, the estimation of G is getting better and better. Okay? And the same observation was made for beta. Okay. So this triangle is ORS, which apparently performed the worst, which consider all data independent. And the red circle is our method taupe, where the square, you can see that is Oracle one, and this diamond is the GRS estimator. You see that our method in general perform very, very close. The red, the circle, and the square almost overlap. So our performance almost like we know what is G and what is F. So it's very close to Oracle and agree with the theory. They are generated from AMA. And also this is the coverage probability. Now you can, so I'm going to skip this part, but this figure just show that our method have 95 coverage probability, nominal level, and the length our set is the shortest one. Okay, I think I have 3 more minutes.
Yeah.
Okay, I want to share you with this. Hopefully some of you can give me some idea how to make this story better, because I know some of you that definitely act part in this. Real data. We will strongly recommend by reviewer to give real data. We don't want to study stock. That is cliche. We want to think about it. We don't want to put stock data. We can do S&P 500. Everybody do that. We want to find something cooler. So we do this. Okay. This data takes the students 3 months to learn. None of us know PM 2.5. So he spent a lot of time to read about it. Hopefully he makes sense. He collect, which we saw before, PM 2.5 concentration on Tuesday, Thursday for each week in 2015, and at 129 monitoring sites from National Air Quality System Network. Then he somehow managed to get daily maximum 1 hour concentration for the 3 air pollutants, NO2, SO2, NOx. I honestly forgot all my chemistry back to high school, so I have no idea what is the relationship between them. The only thing I heard is from Song Xi and other people who do this. And also 2 geographic variable, latitude and longitude. And finally, the proportion of energy consumption of 3 main energy resources. Okay, coal, natural gas, and petroleum. And that for the county where the monitor site belongs to, we don't have the data to the monitor site. This is what I show you. This is the conditional variance of the long-run covariance for the 129 set across the United States. And this is the variance of the energy, okay? So the variance of PM 2.5 with respect to different coal consumption or natural gas consumption. The variability within time series change conditional on the coal and the natural gas. So this hints us it's not a bad idea to use our model. So we fit our model. First, eigenvalue test or our test. We show that k equals 3. There are 3 latent factors there, and could be used. And also we use a test by Jianqing and Liao Yuan and Wei Chen Wang in 2016 to test whether or not G equals 0. They proposed a test to do that, and yes, G is rejected. G is not 0. So you should include the G. Okay. And later you can estimate G and plot G to say, oh, G is not linear. Finally, this is what I want to show. I want to show you. Hopefully this makes sense. Maybe it's not. Okay. If it's not, I just delete that section from paper. This is the confidence interval of the relationship between PM 2.5 and those 6 covariates. NO2 ounce coal, SO2 petroleum, and natural gas. And the red one is ordinary square. Blue one is top. From this picture, you can see that, so it seems that natural gas, petroleum, SO2 has nothing to do with PM 2.5. I'm not sure if that's true. I asked Sun said could be, or may not be. Okay. And NO2 and ounce are also correlated. NO2 is positively correlated, and ounce is negatively correlated. From this figure, you can see that the blue one, which is the top interval, is shorter than the ORS. So it reflects the efficiency we think it's supposed to have. The interesting one is this, the coal. We didn't manipulate data too much. This is what data said. The confidence interval of the association between PM 2.5 and the coal, based on this data, suggests there's no association. Based on our method, suggests there is association, positively. The more coal you use, the more the PM 2.5. Now this not only have a shorter interval, but also shows significance. So from real data point of view, it supports that the top and the model makes some sort of sense.
So you're saying the more coal is used, the higher the variance?
The high PM 2.5.
High variance or
high concentration.
Oh, high concentration. Well, yeah, I mean, I think that's true.
Yeah, but the data at ORS cannot.
This has a bigger confidence interval. Actually, the estimate is higher.
No, but it's included. That is, you need to have uncertainty. You cannot only look at
there's more uncertainty. The estimate is larger with a greater uncertainty.
Yeah, that means the inference is bad. That means
yes, I mean it's less precise. Yes.
Yeah, so that means just like if you predict tomorrow's stock price is $100, but from 0 to 1,000.
No, I understand. I understand. Yeah.
So that is why we see that.
So those. Okay. Never mind.
Yeah, any input from you.
Yeah.
I'm not sure if this is. So that is what we got. So I think this more or less probably perhaps supports that the model and the estimation procedure is reasonable. So quick summary. We propose a model and we give estimation procedure and we show non-asymptotic results, and also we derive the asymptotic distribution for inference. And what to continue? To determine K. Can I determine the K? The answer is yes, we can. Actually, we do introduce a new method based on high-dimensional white noise testing to determine that K, which is very different from eigenvalue-based method. And we also have a concentration result, non-asymptotic concentration result for eigenvalue-based K selection, which is new. Also, can you derive a asymptotic distribution of this F hat? Or give some sort of a barrier in bound? This is an open question so far, which we're working on. And what if the number of covariates diverge? This is a big question as well. Thank you.
Any question? One quick question, maybe?
I want to be back and ask this, I guess.
Any other question?
Hi.
Yeah.
I have a question. So when you were doing the numerical simulations, you had all these detailed theoretical results. Do the theoretical results inform what you see there at all?
So, for example, here you can see that as t getting larger, the curvature probability of our method is red. This small circle is getting closer to the blue one, which is the oracle, 95. And on the other hand, the coverage probability of ORS is very poor, which is this triangle. And the length, however, of our method is always small, which is the red one, which is red circle. It's hard to see. It's always very small compared to other methods. Small confidence length, but reaching the nominal coverage probability. So it's indicating efficiency.
I'm curious if the actual rates you derived actually match what you're seeing.
We didn't have that simulation. That's a good point. We can do some simulation too.
I mean, because you have rates for MSE.
Yeah.
And the question is that analysis?
I think he can quickly. I agree with you. He can quickly get MSE and do a regression to the NLT to see.
I'd be curious.
Yeah.
See if that coefficient of 20 is correct.
Actually, that 20 could be get rid of. Yeah. You just do a little bit more masked.
Okay.
That is because it's all in the log. Yeah, it's all in the log, so you don't care about that. What you only care about is this one. It's this small one.
Okay.
Because delta is this is true for arbitrary delta greater than 0.
Yeah. Okay.
All right, I think we are out of time. So if you have any question, you can still talk to Rick. Otherwise, let's thank Rick once again.